Here we can see a simple electrical circuit which has a battery, a switch, a light bulb and wires to connect each of the three components together. Using the switch, we can switch the light bulb on and off as follows. Let's use electrical symbols to redraw this particular simple circuit. Here we can see we have the electrical symbols for a battery, for a switch, for a light bulb and for wires. When the switch is in the open position as shown here, then no electrical current is able to flow round the circuit. Consequently, the light bulb is off. When the switch is in the closed position as shown here, then we have a complete circuit and electrical current flows around the actual circuit and we can see that the light bulb is on. Let's place attention on the switch. Here we can see the switch is in its closed position. Now the switch is an example of a two-state device. It can be closed as we see here, or it can be open. And I can alternate between open and closed as you can see here. Let's now consider the light bulb. We can see also that the light bulb is an example of a two-state device. It can be switched on or it can be switched off, and we can alternate between the on and off position. Of course, the light bulb is controlled by the position of the switch. When the switch is open, the light bulb is off, and when the switch is closed, the light bulb is on. Let's consider the electrical circuit we have here in the following way. Let's regard the switch as the input and the lamp as the output. So down here I'm going to produce a relationship between the input switch and the output lamp. So down here let's simply write switch, and let's put in brackets there input, and then I'm going to write lamp, and in brackets there I'm going to say output. Now the switch can be in two positions. It can be in the position shown here, which is open, and we can see that when the switch is open, the lamp is actually off. Let's now close the switch. When we close the switch, we can come over here and we can write closed for the state of the switch, and of course when the switch is closed we can see that the lamp is actually on. Let's reconsider this circuit. Let's have a look at the input. Now the input we know is the actual switch. Now when the switch is open, instead of saying open, let's represent that by a binary number, and let's represent that by the binary number 0. Let's now look at the output when we have the input as a 0. Now we can see that the lamp is off. Well, instead of saying off, let's have off represented also by a 0. So here we can see we've got a relationship between the output and the input. When the input is a 0, the output is also a 0. Let's now consider the other state. Let's close the switch. Now instead of saying closed, let's say when the switch is closed we're going to represent that by a binary 1. And we can see that when the switch is closed, i.e. a binary 1, we can see that the lamp is on. Now instead of saying on, let's represent on by a 1. What we now have is a relationship between the output and the input presented using 1s and 0s. Now this is quite handy because when we move on to logic gates in later videos we're going to be talking about 0s and 1s, not open and closed and on and off, but they're really one and the same thing. So when you think of a switch, when it's open, think of it as being a 0, and when it's closed, think of it as being a 1. When you see a lamp that's on, think of it as being a 1, and when you see it off, think of it as being a 0. And we're able to use these memory aids. Let's not take these circuits too literally. They're good memory aids to help us understand logic. and particularly logic gates.